let's just make sure that you guys can see this. So if this is it, and I make, say, that way the y direction, just for the time being, I need an x and a y, then the net force in the y direction is completely known, right? The ladder's not going to accelerate, so I know the normal force in the ground is going to equal the sum of the person and the ladder. So the normal force is going to be 800 newtons. Any question there? Okay, because here's where I'm starting to see a bit of a disconnect as to what I think you should know and what you're demonstrating. The coefficient of friction is 0.9. It was given, and this is supposed to be the coefficient of static friction. Now, we don't know the frictional force. We have a range of possible values for the frictional force since it's static friction. Friction is something between 0 and mu times the normal force, which in this arrangement is going to be something less than 720 newtons. Right? That's how static friction works. Now, in a parallel argument, the net force in the y direction also equals 0. And the frictional force...
You mean in the direction?
Oh, yeah, I do mean x. The frictional force and the normal force on the wall must be in balance. Now I'll go one step further here and recognize that if I choose my pivot to be here, which is not really me choosing, if the ladder is going to pivot, it's going to pivot there. So it's not like it's a weird choice to choose there. The issue here is that this force and this force are both trying to make the ladder pivot this way. Right? Which means in order to keep the ladder from collapsing downwards, the wall has to push the other way. Correct? It shouldn't be a surprise that as the person walks upwards on the ladder, they increase the length of their torque arm. Their weight stays the same, the angle stays the same, but the distance from the pivot increases, so they are applying a greater clockwise torque, which means the wall will have to apply a greater counterclockwise torque. Question about that? That is a fundamental issue here, because there is a clear maximum to how much torque the wall can provide. If the torque from the wall attempts to exceed the normal force maximum, then the wall will attempt to provide a force greater than the torque you can get from 720 newtons. This is the maximum. Right? If it takes more torque than that, and the torque arm length is fixed, the wall might attempt to push with 721 newtons against the ladder. And when it does, the frictional force will break because it tops out at 720 newtons. So the bottom of the ladder will begin to slide because the condition that's met is that the frictional force can't exceed 720. That creates other conditions in the problem. The wall can push more than this. The wall's probably not going to collapse under the weight of the ladder. But the maximum frictional force is balanced by this normal force. That can't be exceeded. If the normal force tries to push more, it's going to break friction at the bottom and the ladder will collapse. So that's what we're trying to show here. Now, I got bogged down in third period having to explain to them how to tell if a torque is positive or negative. And that is a little bit hard for some folks to have the spatial reckoning to do this. They were somewhat disjointed by me drawing the ladder horizontally. Do I need to be a little thorough here? Because I want to know that before I go on, not after. Because I want to do the whole problem to find out I can't tell why you made this positive or negative. So do we need an opportunity to determine the direction of torques here? Okay.
It's not about the direction of the torques. Just like the last thing you said if the torque from the wall tends to exceed.
So when I get back to this, my job is largely done now. I have the mathematics to do, and since my pivot point is at the end, I can now deal with my net torque by recognizing that there are, in fact, 3 torques. There's the torque from the ladder, the torque from the person, and the torque from the wall. And based on what we just talked about, I know that these two have to have the same sign, and this one has to have a different sign. Since this has to sum to be 0, I don't have to worry about the answer being a positive or negative. I am setting this so it sums to 0. Now, 3 torques. So each torque has 3 pieces of information that I must identify. Let's go with the ladder first. This ladder is 4 meters long, so the center of the ladder is 2 meters away from the bottom. That's a torque arm length of 2, and there's a force of 200 at an angle of 30 degrees. That's negative 200, by the way. 200 meter newtons, right? Sine of 30 is a half. 2 times 200 is 400 times a half is 200 meter newtons. Questions? All right, the person. I don't know where they stand. I just have to put a distance there. I put a L. I know that they are contributing a force of, 600 newtons? And their angle is also 30 degrees. Best I can do is write this as negative 300 L. Which brings me to the wall. The wall has a torque arm length of 4 meters because it's a 4 meter long ladder. And I know the maximum force the wall can apply can't exceed 720 newtons. However, this force acts at 60 degrees. So, if my multiplication is right, 4 times 720 is going to be 2880 times a sine of 60. 86% of that. Now, this has to sum to be equal to 0. Your job now is to find L. I don't think that part's particularly hard. Maybe it is in focus and my eyes just aren't. All right. So you work that out. L is going to be what, 7.2 meters?
7.6.
6 meters, all right. You can't stand there. Why can't you stand there?
So that is 4 meters.
So the actual answer is 4 meters. Although 7.6 is what you get from this, it's not a 7.6 meter long ladder. What this tells you is that you can stand anywhere on the ladder and the ladder will not slide. That's what it's telling you. It's not telling you that you need to stand here. You can't stand there. Now, there's implications here, but this is the math. That's not the answer. And that's why we need to be careful about what happens when we solve a problem like this and we get an answer that might exceed our expectations. We expected an answer between 0 and 4. We got an answer that was greater than that. So I think traditionally, students tend to think they're wrong. And don't concern yourself with that. Half of you were wrong. So you have every reason to believe that there's something going on. But in addition to that is your ability to self-identify what happens when your answer is outside what you would expect. This whole thing was predicated on there being a maximum force here. But the normal force from the wall is a reactive force. I'd argue that the normal force from the wall never even got close to 720 newtons. I mean, you could work this problem in the other direction. You could have worked this problem saying, well, I don't know where they stand, but let's assume they stand at the end. And instead of knowing this, don't know that. How much force from the wall would be necessary in order for the person to stand at the end of the ladder? Now, the problem with doing it that way is all that tells you is whether they can stand at the end of the ladder or not. That's probably not what you wanted to know. And if you find out that it exceeds the 720, you'd have to keep finding a place where it won't exceed that. That's probably the long way around. But I'm saying this to all of you, hope that you're not just like hearing me talk, but considering what that means for problem solving in your notes. Where you have to solve a problem, which means you have alternate methods of considering what to do. So if we had done that, if we had put the person at 4 meters, we could have worked the problem that way. Is that the most efficient way to figure out where they can stand? Probably not. But you would know right away whether whether they could stand there or not. You didn't know it would exceed it. Now the fact that it exceeds it, means that I guess any place is safe to stand on the ladder. Not likely true. We made a massive mistake here. A mistake that you're probably not even thinking about.
Friction.
What's that?
Friction from the wall.
No, but I count on the friction of the wall all the time. I mean, the friction of the wall, you realize, helps you from keeping the ladder to slide backwards. It pulls up on the ladder, adding another torque in this direction. And that torque is aiding the torque from the wall in keeping the ladder from sliding out from under you. I like that torque. More than once, that torque has saved my bacon when I've been on a ladder. I'm on a ladder a lot. No, that's not it. That's not the problem. That's not why ladders have the warning. Most ladders, my ladder has spikes at the bottom of it. I can spike it into the grass so that it's not going to go anywhere. There's no frictional force. It's embedded in the grass. I have an infinite amount of available force. Luckily for me, got an infinite amount of me too. No, the problem isn't that. The problem is that 600 newtons isn't the torque. It's not 600 times whatever that L is. My center of mass is not located at my feet. My center of mass is located a meter or so above that, which means that where I'm standing at that point might actually have a different torque than I calculated because it's a different torque arm. When we go back to the picture first, and I'm not sure I understood this problem when I was dealing with it a few moments ago, but the choice for positive torque or negative torque is still arbitrary. It's like asking you, do you want to make anything that's upward positive or do you want to make upwards negative? It doesn't really matter your answer. On the other hand, you do need consistency. Most of you always make up positive and down negative. And there's absolutely nothing wrong with that. It's more difficult here because clockwise and counterclockwise has yet to be something that you would consider positive and negative. But we have to understand that it's not really clockwise or counterclockwise. It's a torque vector suggesting into the paper or out of the paper, or in this case, into the board or out of the board. And like any vector, if it's one-dimensional, there has to be a positive and a negative, a way for us to compare them. Currently, choosing to make into the board positive or into the board negative is still arbitrary. So I'll ask the room, things that rotate in this direction, do you want that to be positive or do you want that to be negative?
Negative.
All right. Now, something pushing this way with a pivot here. Is that going to cause the ladder to rotate in the negative direction or the positive direction? How about that one?
Negative.
So that's not so bad. Now, I have people who don't have the spatial awareness to do that. I don't know why, because I can't understand that. So as your teacher, that's my failing. But you don't have to do it like that. There are alternatives. You could use the books method, which will require that you put together a coordinate system with its origin at the pivot point. You must decide what is positive and what is negative, and then consider your torques individually from there. Now, under this circumstance, this is a little more cumbersome, but if you want a prescriptive way of doing this that doesn't really require you to know the right-hand rule, or in my estimation, have to make decisions, because you really don't have to make any decisions using this method. You just have to follow a procedure. Then your torque gets broken down into only two things that can determine positivity or negativity, and you follow the prescription. If your torque arm is in the positive x direction, then your torque arm is positive. That's the x direction, as indicated by drawing the x-axis along your torque arm. If your force is in the first or second quadrant, it's positive. If your force is in the third or fourth quadrant, it's negative. That combination will consistently give you useful positive and negative for torque. Remember, ultimately, you're going to be dealing with net torque, which means you must sum them, and you must have a method for indicating whether those torques are positive or negative. Now, what I find difficult about the method I just outlined is the method I just outlined does make an assumption that you have to know all the time. You don't get to choose, you have to know. And that is that in torque that is positive means out of your paper or out of the board. If you use this method, this way is always positive, because positive torques would cause it to rotate this way. You don't make a choice here. You must do it that way. So if you guys don't like to make choices, this is your shot right here. It's a prescription. You draw an x-axis in the direction of the positive torque arm. You draw the y-axis perpendicular to it. Label your quadrants. And then from that point forward, any positive torque will be out of the paper or out of the board. Yep.
How do you signify it's out of the paper again?
Out of the paper is a circle with a dot, which I would normally draw right at the pivot point. Again, not the right-hand rule, but the right-hand rule will let you know what direction it turns. If it's positive, you point your thumb in that way, roll your hands, that's the direction it turns. If it's negative, put your thumb in that direction, roll your hand, that's the direction it turns. All right? Of course, none of these are my preferred method. My preferred method is that you know the right-hand rule. And knowing the right-hand rule means being able to deal with your torques and make decisions about the torques in a manner that puts you in a driver's seat and control the problem and allows you to make the decisions about positivity and negativity. That's my preference, is you decide whether a torque in any direction is considered positive or negative. For example, if I choose this one to be positive or this one to be negative, it's me making that choice. And you can use the right-hand rule. The right-hand rule doesn't tell you positive or negative. It tells you direction. So if I want, I can make that way positive, and if I want, I can make that way negative. I don't really care. That direction is into the paper based on the right-hand rule. Right? I curl my fingers in that direction. My thumb has to go into the board. Now I take my right-hand rule, and I know this is going to be weird. Don't hurt yourself. I'm going to turn my paper so that my paper makes it easy for me to use the right-hand rule without having to contort myself in such a way that I break my arm or fall out of my chair. So I'm going to point the torque arm away from me. I'm going to take my three-finger rule here and point away from my body. And then I'm going to choose which force I'm evaluating. I'm going to evaluate the weight of the ladder, which is going to require me to rotate my wrist so that my middle finger aligns with the weight of the ladder. Yeah, I know, it's not perfect, but if I just bend my finger a little bit, I can get them to line up. What I don't want to do is reverse it somehow. I want to make sure my finger stays on the same side of my middle finger. My pointer finger. It doesn't really matter though. You'll notice that no matter how your middle finger swings, your thumb is down. That's because any force that's over here from the torque arm is going to cause it to turn in the same direction. I don't have to have it be perfect. I just have to know that my middle finger is over there. Which means that this is a torque that is into the board, as is this one. On the other hand, actually on the same hand, to look at the torque from the wall, my thumb would have to be up. Each of those provides a torque. And now I just decide whether the dot is positive or the dot is negative. That's my decision to make, and yours. So if you want the dot to be positive, great. That one's positive, that one's negative, that one's negative. But this whole thing is just about giving us a way to be consistent, monitor direction, and communicate our ideas to somebody else in a consistent manner. Why this is a stopping point, I really don't know. But there are 10 minutes, 3 different methods. I will not have time to give you your quiz today. Third period ensured that. I would be really prepared on Tuesday. Do we have a connection there? Okay. Ladder, this torque actually would have to be someplace up here somewhere. Right? And the safety of the ladder is much less about the ladder sliding out from under you than it is you causing the ladder to torque backwards. That's really the concern. Now, if you stand at one of the higher places, you are likely to have less to hold on to and might create a precarious position where there might be a torque about that point for you. And as you fall backwards, you have to go grab onto something which might be the ladder, which might spell doom for the system. We're not usually worried about the ladder sliding out from under us, although I've watched my neighbor do that. But I don't always find my neighbor to be the most...
Intelligent.
There are several of those words that are true. I won't say which ones. I will say that he is scared of ladders, and that doesn't help. When you're scared of ladders, bad things happen anyways. Now, I'm going to pause here. I know what a crowbar is. I do want to point out that third period asked for question number 9, which is a box stacked on a box. And they put the pivot, they asked basically, where's the balance point, is what it came down to. They were unsure of the question. In fact, the quote from Ava was that there was no question, just a picture, which I found to be a dubious piece of information. I was sure there was actually a question. And upon further research, there was. But generally, they had a picture that looked something like this. And this is my version of it. And I don't know what any of the things were, except that this was 4 kilograms and that one was 1 kilogram. And basically, you just ask, where does it balance? This is a fine question. It's actually below the level of difficulty of what we just did if you understand what they are asking you to do. However, you don't have any torque arm lengths to work with, but you probably understand that you will have to put the pivot at the location where the net torque is 0. So good luck. You should do this problem. It's great. It's not that hard, but it does require a thoughtful consideration of where things are. I'll remind you that it's the middle where the center of gravity is for these things. So I bet my pivot is going to be someplace between those 2 dots. But you need to use what they give for the distance in your answer. So just be cognizant of that. Since that cost me the quiz in the other class, that's why I wanted to bring it up, because it was at least reviewed there. And I talk about it at more length at the video I posted from third period. But let's talk about a crowbar. Let's say that I have to remove a nail, which means I have something going on like here with a nail embedded in the surface. The idea is that a nail has a head on the top of it, and then the actual spike portion is below it. So you're going to try and place a crowbar. A crowbar is just an angled piece of metal, and at one end there is like a fork that slides on either side of the head of the nail. So generally the end looks something like this. And then this is the bend part, so that when you look at it, you've got a metal piece that looks like that, and then it curves underneath. Okay? Does that make sense? Can you see that enough from where you are for me to use this? Now, one difference here than the problems we've looked at before. The problems we've looked at before, all of our torques have been on the same one-dimensional torque arm. In a crowbar, they won't, because it's really a lever with an action arm and a reaction arm. There's names for that, and I don't really know what they are for levers, and I really don't care. So let's assume that this distance from here to here is the torque arm length for the force applied to the nail. Because you see, the nail, right now, with nothing going on, the nail is applying a force this way to the crowbar. A small distance r from what is a clear and created pivot point. Because I would like to break the nail out of its indentured servitude. So I will apply a force somewhere over here, which gives me a greater lever arm distance, because I am trying to gain leverage over the nail. Now, if these two torques are balanced, we'll call this the force on the nail. I'm sorry, this is the force from the nail, and this is the force from me. Then the torques, when balanced, mean the nail still doesn't budge, correct? However, as you can plainly see, using my right hand rule, the torque from the nail is out and the torque from me is in. It's true. So, F me times R minus F nail times little r has to equal 0. Now, I know I reversed the direction, but what I'm trying to say to you is that when they're balanced, like they are right now, the net force is 0. I don't know if you realize this, that the force on the force from the nail on the crowbar has to be equal to the force from the crowbar on the nail. So, I get a ratio here. Eventually, I could continue to pull until I exceed the force necessary to move the nail. The forces are balanced until that moment. And if you look closely, you realize that there's a lot more force on the nail because R is smaller. That's how you gain leverage.